Another common series that we're going to encounter will be the geometric series. The geometric series is a series that is based off of an exponential sequence. A common notation that gets used for this will be the sum from n equals 1 to infinity of a times r to the n minus 1 power. If I were to start plugging in some values of n, I would get a plus a times r plus a times r squared plus a times r cubed, and so forth and so on. A is said to be the starting or initial term, and that notation is simply referring to the first number of the series, the first term of the series. R is the common ratio. That's why we use R for it. Now, great question to ask is, under what conditions does a geometric series converge? And if it does converge, can I determine the value? So under what conditions does a geometric series converge? And if so, to what value does it converge? Now with that in mind, I'm going to show you some cool stuff. One minus x is equal to 1 minus x times 1. 1 minus x squared is equal to 1 minus x times 1 plus x. 1 minus x cubed is equal to 1 minus x times 1 plus x squared. 1 minus x to the fourth is going to be 1 minus x times 1 plus x squared plus x cubed. As it turns out, this is a pattern. If I have 1 minus x raised to the n plus 1 power, then I can factor that into 1 minus x times 1 plus x squared plus x cubed, and the powers of x continue to go up one at a time. You'll notice that if I were to factor out an a from the original geometric series, then essentially what I have is this thing, provided that n is going to infinity. So let n go to infinity. Over here on the left-hand side, we would have the limit as n goes to infinity of 1 minus x to the n plus 1. On the right-hand side, I would have 1 minus x times a geometric series. Now, performing a couple of small alterations to this means that the limit, that the sum from n equals, I'm just going to try this again. The sum from n equals 1 to infinity of x raised to the n minus 1 power is going to be equal to the limit as n goes to infinity of 1 minus x raised to the n plus 1 power over 1 minus x. The only way that this is going to converge is if the base of the exponential is between -1 and +1. Otherwise, it is going to tend toward infinity. So this only converges if the base of the exponential is between -1 and +1. Now, as that pertains to our geometric series, What that means for our geometric series is if the common ratio is between -1 and 1, the geometric series will converge. So what I'm going to do is change this x into an r, and I'm going to multiply through by a, and we will have our sum of a geometric series. This will be equal to the first term divided by 1 minus the common ratio. This is the sum of a geometric series formula. Now with that in mind, let's take a look at an example or two. For our first example, we'll do the summation from n equals 1 to infinity of, let's do 3 raised to the n power over 4 raised to the n plus 1 power. Now, certainly not written in exactly the form that we're interested in. So what I'm going to do is write out the first few terms, doing n equals 1, 2, 3, 4, and so forth and so on. So at n equals 1, we would have 3 over 16 plus. At n equals 2, this would be 9 over 64, followed by 27 over 256, followed by 81 over 1024, and so forth and so on. This actually gives me all of the information that I need as far as figuring out the sum of the series. A is referring to the first term of the series, and A in this case would be 3/4. No, excuse me, 3/16. The common ratio, that is, as we go from term to term, by what factor are we multiplying? Well, to turn the 3 into a 9, the 9 into a 27, and the 27 into an 81, the numerator was being multiplied by 3. For the denominator, to go from 16 to 64, 64 to 256, and 256 to 1024, we were multiplying by a factor of 4. Now, additionally, if I had decided to do some algebra with this, it is possible to use properties of exponents to turn this expression into 3/16 times 3/4 to the n minus 1 power. Please feel free to use properties of exponents to expand that back out. So, because the common ratio is between -1 and +1, this will converge. The sum of the series, according to our formula, is going to be a over 1 minus r. A, we just said, is 3/16. R is 3/4. That'll give us 3/16 divided by 1 minus 3/4 is 1/4. And changing this to multiplying by the reciprocal, this will be 3/16 times 4 over 1. The sum of this series will be 3/4. For another example, I'd like to do the sum from n equals 0 to infinity of 3 to the nth power plus 4 to the nth power over 5 to the nth power. Now for some perspective, if I plug in n equals 0, I would get 1 plus 1 over 1. If I plug in n equals 1, I would get 3 plus 4 over 5. If I plug in n equals 2, I will get 9 plus 16 over 25. 9 plus 16 is 25, so that'll be plus 1. Plug in n equals 3, this will be, oh boy, 91 125ths. I really can't emphasize enough, this is not a geometric series. What we're going to have to do instead is break this up using properties of series. This would be 3 to the n over 5 to the n plus 4 to the n over 5 to the n if you break it up at its denominator. According to the properties of series, since we're just adding a bunch of things together anyway, I can group this so that the first series is all together and the second series is all together as well. This is now the form of a geometric series, and this is now the form of a geometric series. For this geometric series, our first term is going to be what we get by plugging in n equals 0. Your first term is going to be 3/5 to the to the 0 power. That is 1. The common ratio is the base of your exponential. That'll be 3/5. For the second series, first term is going to be equal to what we get when we plug in n equals 0. That'll be 4/5 to the 0 power, which is 1. And our common ratio is the base of the exponential. If we apply the summation formula for both of these series, this will be 1 over 1 minus 3/5 plus 1 over 1 minus 4/5. Simplifying each of these, this will be 1 over 2/5 plus 1 over 1/5. This is 5/2 plus 5. Getting a common denominator for these, this will be 15/2. That'll be the sum of this sum of geometric series.